This section focuses on the analyze phase. In Chapter 4.3, we learn how transfer functions and predictive models are used to understand relationships between inputs and outputs, analyze data patterns, and predict future performance for better decision-making. Chapter 4.3 explains transfer functions and predictive models. It covers y equals fx modeling, statistical analysis, regression, DOE, and tolerance design. This chapter is the analytical backbone of DMADV, linking design inputs x's to customer outputs y using data, statistics, and experiments. This slide explains why Chapter 4.3 is important in DMADV. We identify which inputs x's affect outputs y, measure their impact, build predictive models, optimize x's, and set tolerance limits. The key question is, if x changes, how much will y improve? This helps design robust and reliable products and processes. This slide introduces y equals fx modeling, also called the transfer function. Here, y is the output or CTQ, x's are input variables, and f shows their relationship. The transfer function explains how changes in x affect y. In DMADV, this helps predict performance, identify critical inputs, make data-driven decisions, support design optimization, and link engineering parameters to customer requirements. This example shows y equals fx in a bank loan process. The output y is loan approval time, influenced by inputs like data quality, automation, number of approvers, and system speed. The model indicates that data quality and automated checks have the strongest impact, while others have moderate effect. Therefore, automation and data quality become key design focus areas. This manufacturing example explains bottle filling. The output y is volume accuracy, affected by nozzle pressure, liquid temperature, viscosity, and machine speed. The model helps identify the right combination of inputs to reduce underfill and overfill, forming the basis for DOE and process optimization. This slide covers statistical analysis of inputs before building y equals fx. Inputs can be continuous, discrete, or categorical. We analyze their distributions such as normal, log-normal, exponential, Weibull, binomial, or Poisson to understand behavior. This is important because different distributions require different statistical methods. This slide explains descriptive and correlation analysis. Descriptive statistics like mean, median, variance, standard deviation, range, and percentiles help understand input variability and its effect on y. Correlation analysis shows the strength of relationships between x and y and among x's, helping check multicollinearity, for example, system response time versus customer dissatisfaction. This slide explains descriptive and correlation analysis. Descriptive statistics like mean, median, variance, standard deviation, range, and percentiles help understand input variability and its effect on y. Correlation analysis shows the strength of relationships between x and y and among x's, helping check multicollinearity, for example, system response time versus customer dissatisfaction. Regression analysis, used to understand how changes in input variables x affect an outcome y. Simple linear regression, one input variable predicts one outcome. Example, loan processing time predicted by % automation. Multiple linear regression, most common, multiple inputs affect the outcome. Example, delivery time influenced by inventory level, route efficiency, number of vehicles, and weather conditions. Outputs, strength of each input, predictions, and a regression equation for y. Logistic regression, used for predicting binary outcomes, for example, fraud. Yes, no. Inputs can be transaction value, location, customer history, etc. Nonlinear regression, used when the relationship between variables is curved or complex. Example, relationship between temperature and viscosity. His slide explains why regression is critical in the DMADV methodology. Regression predicts the output Y based on multiple inputs X and shows how much each factor affects the result. It provides a mathematical equation that can be used for simulation, optimization, and cost reduction. The example equation shows positive and negative effects of different inputs on Y from the interpretation x1 increases Y, x2 decreases Y, and x2 is the strongest driver. This regression equation becomes the transfer function used during the design phase. This slide introduces DOE design of experiments as a key tool for designing optimal parameters. DOE helps identify the most influential inputs, optimize their settings, and reduce variation. It enables fine-tuning of design parameters to build a robust and reliable design. In DMADV, DOE allows testing multiple factors together and understanding their interactions. It improves prediction accuracy while reducing the number of tests compared to trial-and-error methods. This slide explains the types of DOE used in DMADV. Screening designs are the first step to identify the most critical factors from many inputs. Full factorial designs study all factor combinations and are best when the number of inputs is small. Response surface methodology (RSM) is used for optimization and fine-tuning. RSM helps find the best combination of X's, identify maximum or minimum Y, and detect curvature effects. I prefer this response. This slide covers advanced DOE approaches under transfer functions and predictive models. Mixture designs are mainly used for chemical and formulation-based experiments. Taguchi designs focus on noise reduction and improving robustness of the design. DOE outputs include main and interaction effects, regression models, and contour plots. These outputs help identify optimal settings and prediction ranges. Overall, DOE results support robust design and tolerance development. This slide explains tolerance design, a critical part of DFSS. It defines the allowable variation in materials, dimensions, process parameters, and performance. The main goal is to keep performance within CTQs despite natural variation. Proper tolerance design makes the product robust and reduces defects and failures. It also helps control cost and ensures consistent performance in mass production. This slide explains the types of tolerance used in predictive models. Functional tolerance ensures the product works as intended, like proper fit and clearance. Manufacturing tolerance reflects variation due to machine and process capability. Statistical tolerance analysis combines variations from multiple components using models. This approach helps predict overall variation and improve design reliability. This slide outlines the steps in tolerance design. First, identify critical to quality characteristics or CTQs. Next, determine key input factors affecting CTQs using DOE or regression. Define acceptable variation and set clear tolerance limits. Validate tolerances through simulation like Monte Carlo analysis. Finally, balance cost and quality to achieve best performance at lowest cost.